turns on in this building, then maybe we have to suspend a little bit because it's a bit noisy. But otherwise, we will just. Final functions, please.
Thanks very much, and thanks to the organisers for including me in what has been an absolutely fascinating workshop. So I'm going to go beyond matroids and talk about some generalisations of them, a couple of generalisations. The first one, the starting point, is the relationship between the rank of an incidence matrix over GF2 and its row space. So an incidence matrix of a graph as our starting point has rows indexed by vertices, columns indexed by edges. The entries are 0 or 1, and they just indicate whether a given vertex is incident with a given edge. And we're letting E be the set of columns, or a set indexing the columns, and suppose that W is some particular subset of this ground set that we are interested in. And every subset of the ground set has a rank, of course, being the rank of the submatrix defined by its columns. Having presented a matrix over GF2, we will try and set a good example to our undergraduate students by putting it into echelon form. So let's do that, and with a bit of rearranging of columns after doing that, it'll look like this. The number of rows of the matrix overall will just be the rank of the ground set. The rows in this group here, there'll be the rank of E minus W of them, because that's what the rank means. But these rows over here are interesting. They are a set of rows that generate the subspace of the row space whose members are all 0 outside W. So think of vectors where the positions outside those indexed by W, the entries there are all 0, and they form a linear subspace. And the rank of that subspace will be the difference between these two ranks. And we can count that. And because it's over GF2, we get this as the expression for the size of that subspace. We can count that subspace more naively if we imagine we have an indicator function for the row space, which takes value 1 if a given subset is in the row space and 0 if it isn't. And I guess talking about subsets being in a row space, I'm smoothly going over to the characteristic vectors over GF2 of those subspaces. But if we imagine, an indicator function of the row space, and we simply add up all its values over subsets of W, then that's another way of counting the size of the subspace of the row space whose members are 0 outside W. So we get this equation, and I'll put it high up again on the next slide, repeating it. If we turn that around to make the rank as the subject of the equation, so we get a formula for the rank in terms of the indicator function of the row space, this is what it looks like. And I guess, Jeff was referring in his talk to papers of his that he did a long time ago, so I'm trying to break his record for being the oldest sort of self-citation in the conference. So back in 1993, I tried to generalise this to arbitrary functions, any function on all the subsets that doesn't have to be the indicator function of a linear space, because this gives you a way of assigning something that can play the role of a rank. Now, it won't necessarily obey the rank axioms, but if you kind of turn a blind eye to that and you look at contexts where you like to use rank, you can just try this rank formula and see what happens. And so that gives you this expression, and I call Q the rank transform. It takes any binary function. By a binary function, I just mean a function defined on subsets of the ground set, which can take any complex value really, although for indicator functions of a linear space, they're just 0, 1 valued, but we consider them more generally than that. A bit of an issue over whether this is always defined, and it isn't, but we'll come back to that. Note also that this rank transform, the result you get is the same if you apply any scalar to this binary function f. So it's invariant under just scalar multiples of the binary function. We can consider binary functions to be equivalent if one is a scalar multiple of the other. Generally, I use that fact to, whenever I get a binary function, to scale it so that its value on the empty set or the empty vector is 1. But it's also convenient sometimes, and interesting in view of what I'll say later, to scale it so that its size as a vector is 1. Okay, I'll come back to that later. Okay, so having got a rank function, there's a standard expression for rank duality, which can be used in contexts more general than matroids. It's matroid duality generalized a little bit. Another classical combinatorial duality is the Hadamard transform, which is the n-dimensional mod 2 Fourier transform, essentially, also known as the Walsh transform or the Hadamard-Walsh transform, and that's got history in the world of binary matroids too, because the Hadamard transform takes linear spaces over GF2 to their duals. And interestingly, this Hadamard transform and the classical rank function duality formula are just two different manifestations of the same underlying duality. In other words, this diagram down the bottom here commutes. If you do the rank transform so that you've got something rankish, and then you take the matroid dual or use the matroid duality formula with this little modification at the end, that's the same as if you apply the Hadamard transform and then do the rank transform. Same, at least up to a constant factor if you need that. So we have this nice duality going on, even though our rank transform won't necessarily give us a matroid rank function in general. Okay, so we've got a rank transform which gives us something like a rank. We've got duality. We also have minors. And this again is, I mentioned that the rank transform, or at least I had on my slides, that the rank transform is related, well, technically slightly more general, but related to ideas of Joseph Kung going back to 1980, and so is this minor construction as well, where contraction has this expression, deletion has this expression. You might wonder what those expressions have in common. But anyway, those expressions play nicely with the rank transform. Contracting and transforming is the same as transforming, then contracting using the matroid contraction formula or the matroid rank function contraction formula, and we've got the sort of commutativities between of deletion and contraction that we would want. So we get a theory of minors as well. Here's an example of calculating the minor. So here is a little binary function. This is just the graph with two vertices, two parallel edges between them. Yes, question?
So for the previous slide, the definition of contraction, does it depend on E?
Yes, it does. The question, well, it depends. Yeah, that's a good question. So this expression for contraction, for contraction to work, X has to be a subset of the ground set with E removed. So you're really just, with appropriate scaling, you're really just restricting, really, the binary function f to those subsets of the ground set that don't contain E. Yeah, it's a good question. Thanks for that clarification. And likewise here, over with deletion, x is a subset of big E minus little e, again. Okay, here's the calculation. When we contract, we essentially just take the top half of the vector representing the binary function. Imagine a sort of tabular form of the binary function. And we get this. And that's the binary function representation of a loop. And here we get a co-loop. If we delete one of our edges, that's what we get by adding the top half and the bottom half of the binary function together. So that's all sort of standard stuff, just expressed in terms of binary functions, just so you know how the minors work. Duality in these minor operations work well together. As I mentioned, duality in the binary function world is the Hadamard transform, and we can imagine doing minors on each side, and the relationship between them is that is exactly the usual sort of relationship where doing duality and then contracting is the same as first deleting, then doing duality. And when you've got a theory of generalized that generalizes matroids where you've got some duality, some ranks, some minors, especially what do you do with them? And my first introduction to this area was to try to develop a theory of Tutt-Whitney polynomials or functions, because the exponents aren't always non-negative integers, and that developed in a series of papers. I'd like to pay tribute at this point to Dominic Welsh, actually, because he first got me interested in the Tut polynomial when I was a doctoral student with him, and in my very first year he had this diagram of the Tut plane showing how much information it contained, and I was astonished and fascinated, and perhaps slightly surprisingly now, I didn't then go on and do my doctorate in that area at all, but it was Dominic's enthusiasm and vision is very infectious and inspiring, and it stayed with me actually, and I returned to I came to explore Tut polynomials well after my doctoral days. I'm grateful for him for inspiring that. Another thing you can do with, if you've got minors, is to look at excluded minor characterisations of classes of interest. And this was a suggestion. I was once talking about this work with Joseph Kung, who, as I mentioned, some of his work was kind of presaged what I was introducing, and I asked him sort of what's a next natural area to explore, and he said, and he's a deep thinker, he said excluded minors. So some years later I suggested this area to one of my doctoral students, Ben Jones, and he did some really good work on that, which I'm now going to summarise. It's available on the archive. So if we take the whole, in a Venn diagram, if we take the whole class of real valued binary functions, so I'm slightly restricting here for some simplicity, real valued binary functions, there they are. I mentioned before that some of the formulas I've introduced for rank and minors aren't always defined, so we'd like to know when they are defined. If all minors are defined, then the class of binary functions in which all minors are defined, Ben showed, was the class of binary functions that don't have this binary function as a minor. It's a stronger condition to ask for the rank to always be defined. And again, Ben was able to characterise that within binary functions by showing that the excluded minors, are binary functions of this form, but with any alpha less than or equal to -1. Okay, so if we're within the class of rankable binary functions, we know then everything's defined, so we can talk a bit more freely, I guess. Let's remove those two classes, but keep as a reminder the minors that we are excluding. And Ben has some characterizations of other classes. He characterized all K polymatroids, the class of K polymatroids for all K, using excluded minors in this way within the class of binary functions. Let's illustrate that with his characterization of two polymatroids, which are those binary functions that don't contain as minors the ones we've mentioned already, plus these. So there's some extra ones of dimension 1, and there's 4 specific ones of dimension 2, or ground set size 2. Within the class of two polymatroids, he was able to characterise matroids as precisely those that don't contain this binary function as a minor, and that's just the binary function version of the graphic two polymatroid of K2. So if you've got the class of two polymatroids and you exclude that as a minor in the sense we're using minors, then you get precisely the class of matroids. So if you've spent all week wondering what on earth matroids are, now you know. Within the class of matroids, he also used his techniques to come up with a nice new proof of Tut's characterisation of binary matroids within the class of matroids, being precisely those matroids that don't contain U24 as a minor. He has a new proof of that in his work, so that was really exciting. So that's the latest developments on this theory of binary functions. I now want to, in the time remaining, talk about another generalisation, and now we're looking at the binary function versions of deletion and contraction. And I'm going to look at those two expressions for deletion and contraction. There they are at left and right. And we're going to interpolate between them using some parameter lambda. Okay, so with this parameterized minor operation, this lambda minor operation, lambda equals 0 gives contraction, lambda equals 1 gives deletion. You can have any lambda. I've sort of put lambda in the unit interval in this picture as a kind of a scale that you can use to interpolate between deletion and contraction, but you can go much more. You can basically use any complex number as a parameter, and you'll get a reasonably well-behaved minor operation. There's a rank transform that goes hand in hand with this minor operation. So we have a slightly different parameterization now, but the lambda and the mu have a simple formula between them. I don't want to dwell on the details of the formula here. It's quite complicated, but it does turn out to be the right way of defining a rank transform for these generalized minor operations. If mu equals 1, we just get the ordinary rank transform. If mu equals -1, we get its dual. And this leads to another theory of generalized Tutt-Whitney polynomials, and I like to think it pays its way a bit. I mean, if you go introducing a generalized Tutt polynomial, you really have a bit of an obligation to show that it contains some information that's of interest, that in fact was previously of interest. And I was able to show that the partition function of the symmetric Ashken-Teller model from statistical physics, which is a relative of the Ising and Potts models, although that is not captured by the Tutt polynomial, it is captured by these generalized Tutt polynomials. Once again, we have Hadamard transform playing the role of duals, and for what I'm about to describe, I want to represent the Hadamard transform in a matrix form as a Kronecker power. So it's well known that if I want to express the normal Hadamard transform in terms of, in a linear algebraic way, where the f, the binary function f, is given as a vector of length 2 to the n, and so will its dual be. Well, I've got a great big matrix for the Hadamard transform, known as the Sylvester-Hadamard matrix, which is the Kronecker power, the nth Kronecker power of this little 2x2 Hadamard matrix. So that's a way of representing this transform that's going to be convenient for us. It's the standard Hadamard transform has this factor, or at least is fairly traditional to have this factor out the front, but if you want it to be a unitary transformation, which is a nice thing to be able to do, so everything's on the same scale as it were before and after applying the transform, then we scale the matrix. Instead of using the standard little 2x2 Hadamard matrix, we use this one, scaling it by 1 on root 2, so that you get a unitary matrix, and then you have what I'm going to call the unitary Hadamard transform, or the normalized Hadamard transform, and I'll write it like this, with the H2 matrix with a little mark over the top, and I'm going to call that transform L-1 of F, because it's a special case of a family of transforms. And again, I don't want to dwell too much on the significant technical details in this family of transforms, but we have a whole lot of transforms here, one for each complex number mu. Again, it's convenient to express them in Kronecker power form, where this time we use this particular matrix. And some special cases, this matrix is unitary precisely if mu, our parameter, is on the complex unit circle. Mu equals 1 is the identity, mu equals -1 is the normalized Hadamard transform. These transforms interact nicely with each other in the sense that if you compose them, that's just like multiplying their complex parameters. You get other things that you like to see in Fourier-like transforms, like Plancherel's and Parseval's theorems, and they work well. They interact well with the generalized rank transform and generalized minor operations. I just want to present a couple of little results. They depend on the machinery that I've set up, so there's a lot of machinery that we've gone through pretty quickly as an overview. But what I found that you could answer a simple little question about the Hadamard transform using this machinery. The Hadamard transform is an involution in the sense that if you apply it twice, you get back the same thing. You get back, it's just the identity then. So a really simple involution on any complex vector is just to take the complex conjugate of each element of the vector. So the element-wise complex conjugate. So I asked, when does the Hadamard transform, or the normalized Hadamard transform, amount to nothing more than just taking the complex conjugate of every vector, of every element in every position of the vector? And once you've got this machinery set up, we can say that the normalised Hadamard transform has this property if and only if there's a real valued binary function such that our function f can be obtained from that real valued one by applying this transform with the parameter I. Okay, so that's an interesting property of the parameter I, or at least the transform indexed by the parameter I shows that something more is going on with these transforms than just having the identity and the Hadamard transform. And there's a few lines of proof that I will skip for the sake of time. Another thing I was able to do was to look at how these generalised transforms relate to, to express them as combinations of identity transforms and normalised Hadamard transforms. And the 2x2 matrices that this 2x2 matrix is obtained from are combined to give this matrix in the proportions alpha mu and beta mu given by these formulas. Interestingly, these numbers add up to 1, but perhaps more importantly, the sum of the squares of their magnitudes add up to 1. So they really do act like probabilities. These are complex numbers, not particularly acting like probabilities, but these act like probabilities. They look suspiciously like probability amplitudes. And we're able to show that the transform of f for an arbitrary complex number on the unit circle is just an appropriate mix of partial Hadamard transforms where the weightings of the numbers of the partial duals are just appropriate combinations of these numbers alpha and beta. So I've got a bit of an illustration here of what happens if we move mu, our parameter, around the unit circle and what happens to these parameters alpha and beta that specify that mix. You can see that the complex numbers defining alpha and beta are always at right angles. And we show that, you can show in a few lines, and I won't go through this again, the result, I had this on the previous slide, that the mu transform, where mu is on the unit circle, is just I'll call it a quantum superposition of all the partial Hadamard transforms, because that's precisely what it is. The coefficients give us our probability amplitudes, or the amplitudes whose magnitudes and squares become, or squares of whose magnitudes become probabilities. And in the special case when mu is plus or minus I, all the amplitudes have the same magnitude. So all the different partial duals have an equal probability of being chosen if you observe this quantum superposition. I must close quickly on about 30 seconds worth of non-technical material, seeing I've spent some time talking about the unit circle. This is a solar halo that you would normally see in colder latitudes, but I saw this yesterday here. So that was pretty interesting. Having seen talks by Carolyn and Ian, I was very pleased to see a Möbius band just down the road outside the Science Museum. And of course, I need to finish by paying my respects to the hospitality here in Daejeon by paying my respects to their mascots, Kumdori and Kumsuni. Thank you very much.
Thank you. Any questions?
You defined this interpolated minor operation. Do you know any examples where you can take a matroid and apply something between deletion and contraction and stay a matroid?
Yeah, that's a really good question. I've wondered about that. I haven't got a good example of that. If you stay on the unit circle with your parameter that defines this minor operation, you'll get some sort of superposition of things, but you don't seem to get an elegant, unique thing. So you have to kind of be content with a superposition of all partial duals. And that's something that's kind of nice, but it's not just one single object, one single matroid. That's if you stay on the unit circle. If you go off the unit circle, you seem to, in some sense, lose information. Things aren't so elegant, and I doubt that would lead to something of particular interest, but that's where I'm at on that. Don't have a final answer. It's a good question, thanks.
Any other questions? So if not, let's thank the speaker again. Yeah.